And as I have been dedicating each lecture to somebody who has played a significant role in where the technology of artificial intelligence stands today. So my today's dedication is to this guy who is Cloud Shannon. And those of us who have studied digital communication know that how important a person he is. And I would urge everyone to uh, must click the link to find out more about him. This is an article which was published in IEEE Spectrum, though he died in 2001. But the information uh, theory or the information technology is uh, based on his very remarkable work, and especially his paper, which he published as a part of Bell Lab in 1948. It's called A Mathematical Theory of Communications. And then he basically introduced a term, entropy, taking it from the probability and thermodynamics and make it a measure of information. And that is very important. And it is important even for machine learning as well. So, and he also coined the term bits as we know it today, that bits as a unit of the logic of 0 and 1. So, with this, let us quickly review the week 4 that we learned about the policy, UAE AI policy, and how vibrant it is, and how they are basically changing the complete landscape of United Arab Emirates and especially Dubai. And it seems like it may no longer be just a tourist destination, but it's going to be a center of excellence in artificial intelligence, and the way they have strategized. And primarily, they have implemented the strategy. That's even more important. And I shared with you the GITEX, that all the companies who were presenting in GITEX, how almost everybody is focusing on AI. Even the Oracle has now this completely new ERP, and everything is centered around generative AI. And so are Intel, Google, and all these big companies, network companies. They all are focusing on AI. That has also like taught us that AI is going to play a significant role, and even the established players, if they don't really incorporate AI in their products, I don't think so they can even sustain their businesses, or because uh, the way AI is just molding, changing everything. So then we did some exercise of code generation for dimensionality reduction. I gave you an assignment as well. We learned about Bayes theorem, and then several KPIs, the measures of the um, applicability of artificial intelligence, which is sensitivity, specificity, accuracy, true positive, true negative, false positive, false negative, F1 score. So we studied all of this. And then we again also generated code to understand ROC, that how you basically plot an ROC and how to operate on the ROC curve. And then we started learning about random variables. And I also told you that learning about probability distribution is very important, because generative AI is all about the distributions, the data, the probability distribution. Having a strong background to really understand what, so that's why I spent a little more time on learning about the probability distributions. And then I also shared with you work of one of my PhD students, where we basically modeled some of the real data using some of the distributions which we could find and nicely fit into the data, and how could we actually generate a nice application on that. Today is I would like to work on the joint probability distribution function, where things start getting messy, and then that's why it requires a lot of computational power to learn about the probability distributions, as now they are jointly interacting with different features in the data, and that's something difficult to get. Today, I also intend to cover uh, generative adversarial network, which are GANs, that how they relate to the probability distributions. And we just keep learning about generative AI, the concepts in generative AI, where we also study the fundamentals. So we will spend some time learning about GANs, and then stochastic processes, stochastic models, and how they are important in modeling a real life scenarios. Uh, and we need to learn about information theory, where the Shannon becomes important. That how information theory plays a role in AI. So it's going to do that. And if we find time today, we'll do decision trees as well. Clustering perhaps will not get time for it. And then I'll also share the work of another of my PhD student on decision trees, and how we can basically augment decision trees using AI and finding out what the data is saying to us. And so, so with this, let us start by just going through the distributions and joint distributions. Okay. So though it is all about data, and as we have initially pointed out that you have real life problem scenarios, and you are getting data which is in terms of x1, x2, xn, as we can see it here. And then the probability of occurrence or the frequency of occurrence of each outcome, you can easily measure whatever are the outcomes. For example, if this data is about people voting in an election, so you can find out how many people are voting for a particular party. So that will help you to find out the probability pi. So probability pi is that how many people have actually voted for party I divided by the total number of votes which are counted in the election. So that will give you a probability that a person, once he comes for vote, what is the probability he's voting for a specific party. So from a real life, you can find out a probability distribution. It's very simple. That from the real life, just keep counting on the occurrence, and usually the process we are interested in will be occurring again and again and again. Whether it is a hospital, patients are coming, whether it's a COVID where patients are coming. If a hospital may have a bigger sample space where a person may be coming with a heart attack, or somebody is coming uh, for an orthopedic treatment, or but again, it is finite. The sample space is finite. So you just keep counting, and then you can easily find out the probabilities. And once you know the probabilities, then you can find what is the average, okay, of that data, what you are receiving, and you can find the standard deviation as well, which is that every data you subtract it from the mean and square it and multiply it with uh, its respective probability. It gives you. So we are going to spend a little more time in learning about what is the significance of mu and sigma square, and so from here we basically extract a probability distribution, which, as I mentioned, is very simple and straightforward. That from data you make histograms, from histograms you make probability distribution, then you fit a curve and you say this is the probability distribution. Once you have the distribution, once you know the distribution, then you can do better prediction, better modeling, and usually distribution means finding out mu and sigma square, and which particular distribution which people have already learned, like it's a gamma distribution, or it's a Gaussian distribution, a uniform distribution, or this distribution, or that distribution. That will help you to characterize the entire data using few parameters. That only with few parameters, you don't have to store the entire data. Once you model it, then few parameters are enough to describe that data, to generate more, to take decisions. So that's why it also basically compresses all the data that you're getting. If you have a model is always something which is very small, very neat, and you can just use that. For example, if it is a sample data of a sinusoid, okay, instead of just storing the entire sinusoid data, if you can only find out what is the frequency, amplitude, and initial phase. So with these three parameters are enough to regenerate this sinusoid. You don't have to, because that is the model. That model puts the math into the data. And once there is a maths into the data, then you only take the maths, and that helps you to do the prediction and decision making, provided maths fit in. Okay, it fits in. If it fits in nicely, you say, oh yeah, now I have a formula, so I can use that formula. And what this all generative AI does is that it makes you less worry about putting an exact math. You let uh, the humongous amount of data and all this neural networks to take this worry that how should I find out which formula to fit in. Okay, obviously in a sinusoid you cannot put a formula for exponential because it's not an exponential. If you try to put that, it will not work. It will just give you a large error once you say how good my model is. So always you got to go back and see how good my model is. So from the model you generate data and you have the real data, and then you can really find out that how good your model is. Can you generate the data from the model? If not, then means your model is not good. Either there is no model that fits into the data, it's chaotic, or perhaps your model is not right. Okay, so it's a lot about uh, the distribution. So perhaps you don't really have to go directly and rely on generative AI and the tools. If you can see a distribution, it's better just use a formula for the distribution. So every distribution will help you how to basically model it, how to find out mu, how to find out sigma. If the other parameters, alpha, beta, gamma, there is a formula. So if there is a known distribution, means there are formulas for you to find out the parameters. It is parametric models, mean only 2 or 3 or 4 parameters define the whole model, what you see here, whatever whether it is binomial or geometric or Poisson or Bernoulli's, or so people have worked on these distributions from real life problems, real life examples, right? So a real life examples is taken into something which is so standard that you can just use a formula. So it's not other way. It's not that you have a distribution and then you're finding a case in reality, in real life. So this is what happens in real life. Okay, and collecting a lot of data and just doing experiment as we were doing tossing of a coin again and again and again, then finding out, oh, once you toss a coin, it is 50% chances that you get a head and the 50 that you get a tail. So similarly, rolling a dice is a simple example that you do a lot of experiments and you find out, wow, this is the distribution. It's a uniform distribution for rolling a dice, that any number can come and the probability 1/6. So if you roll it 10,000 times, and then you will realize there is a formula. So you don't have to do 10,000 rolling. There's a formula which says probability of getting every digit is 1/6. So there is a formula for almost everything that happens kind of in reality, in real life. And this is what people have figured that out, plotting all these histograms. And from the histograms, they can see, oh, it seems like this specific distribution. Okay? And as I gave you example of my PhD student, where we have the data of the patients spread into different categories and how often they go to the hospital for a treatment, and where the insurance has to pay their money, but the company is paying for their insurances. So that now you can have a better decision making because you know the underneath statistics. And I also told you that interestingly, the number of heart attacks, number of accidents, number of deaths, they all are almost the same. With the same proportion, they change. So means there is something in the nature which is just making it mathematical, something in the nature that it's making kind of, but only we have to understand all the aspects. Sometimes we can, sometimes we cannot. For example, earthquake, still people cannot figure out why earthquake comes. Perhaps they don't have the measurements of the things that basically makes an earthquake to come, but for the weather they have figured it out. Okay, because they have figured it out for the weather, so you can very accurately predict the weather because now they know the underneath science. So everything kind of is mathematical as well, and provided we know all the external factors. So these are like the simplest distribution is that you have only two possibilities: either you are successful or you are a failure. Okay, so this is called Bernoulli's distribution, where there are only two possibilities: probability of success is p, and probability of failure is 1 minus p. So this is, you can easily plot, like if and I'll go to this website where you can actually play with all these distributions, and so that will give you a better understanding. For example, if you go click on this, so it will open up so because people have been working on this for so many years, so you can have these this is probability 1 is the p, and this is 1 minus p. So you can actually change this. You can move it up and down, and once you move it up and down, the other one will also move. 1 minus p will also move. And for example, if you click on this thing and bring it down, so it is, you can see that things are moving, and you can plot the CDF as well. Remember, CDF is the cumulative distribution function, where here probability is 0, then this is for failure and this is for success. So you can have PDF or you can have it for the PDF, and you can play with this. Once the probability of success goes to 1, the probability of failure definitely goes to 0. So these are the things that you can, this is the simplest one. Uniform distribution is also very simple, that every event has equally likely chances of happening. Okay, in life, so there may be cases like perhaps Pakistani players scoring is an equally likely probability. Not scoring is an equally likely probability that they would not score more than 10 runs. So this is, you can say they are uniformly distributed, whether it's a batsman or a bowler, but it's like equally likely to for them to. So equally likely means that for everyone there is an equal probability of success, or whatever you want to call it. Okay, so it's just distributed over this round, like you're rolling a dice, so it is 1/6, 1/6, 1/6, 1/6. Okay. This is interesting. The binomial distribution is interesting, where you have n trials. So n matches, for example, you play 10 matches. So what is the probability that you will win 5? What is the probability you will win 4? Okay, and based on definitely success probability of you winning 1 will help you to find out that what is the probability that you can win 4 matches. Okay, so there is, like, on average, let's say you win 6 out of 10 matches. So you say my probability of winning is 0.6, 0.6. But still you may not win any. Still you may only win 1 or 2 or 3. So people have actually studied, that's the interesting part. That saying that average is this does not mean that every time you play 10 matches you are going to win 6. There is always a possibility you don't win any. Okay, there's always a possibility then you win all the 10. It's a less possibility, but you cannot say there is no possibility. Okay, so because of all these uncertainties, so if you go on to this one, it's very interesting that you can again see this, plot this, and here is that the probability that you win. Let's say you win half time and you win half of the time you lose. Okay, so probability of winning P is 0.5. Half the probability. So now you can say, okay, what is the probability that I win 8 matches? Though you should, out of 20, you should win 10. If it is not probability, it is just exact score. But no, people have actually learned that no, it is not like this. If we say that the probability of you winning is 5, you can still win less than 50%. You can win 8 and probability 0.120. What is the probability that I win 10? So if you move this, so you can see the probability of you winning 10, 11, 12, and it is showing you that probability. Obviously, because you can win half, so it must have taken a lot of effort for you to lose every match. Okay, so that says very little probability that you lose everything, because you should win half of the matches. But there is a probability that you lose every match. You lose only win 1, you lose 2, you win 2, you only win 3, 4, 5, 6. So probabilities are there. So they are distributed, and they are distributed binomially. It's a binomial relationship of your success out of so many trials based on the average that you have. So this is also very interesting probability distributions. And you can, as I mentioned, you can change the number of matches, and you can change the the one you want to see, that what is the but it tells you 0, 1, 2, 3, 4, 5, 6. Obviously highest probability is that which matches with this, that you have 10, you win 10 matches out of 20, you win 10 matches is the highest probability. But The closer are 9 and 11 also. But as you keep moving away, the probability is there, but it's just not that. So this is the binomial. Poisson distribution is that it's, for example, it's a good example. Let's say the average number of goals in World Cup is 2.5. Okay, so average goals, averaging over all the matches, and you say that it is 2.5 every match, there will be 2.5 goals. So you can figure out what is the probability that there will be no goal in a match, or a 1 goal, or 2 goal, or 3 goal, or 4 goal. So you can have a probability distribution which will vary like this. So 2.5 has the maximum probability, but still a match can have 3 goals and 4 goals and 5 and 6 and 7 and 8, or maybe 0 goal and 1 goal and 2 goals. So it's a distribution. And so this is also an important distribution. So similarly, I have given you a link. So if you go to this link, you can find out by changing some of the parameters, you can play with the probabilities. Okay. Most important for us is the Gaussian, which we studied, the Gaussian distribution. The Gaussian distribution is where you have a Gaussian curve, and you can change the average. For example, the average means this curve will move on this side. Okay, so average weight of the babies may move a little, but it'll still remain Gaussian. And this is the standard deviation, may change a little. So as it is more spread, so deviation means spread, that how much spread is there. So means that it's just varying all over the place. So it's not like very, so if weight varies from 1 pound to 6 pounds, so it means a lot of spread. But if it is not a lot of spread, you say here is very little spread. So everyone is in this range. So perhaps if we think about the income and you say people living in F6 sector, it may be a curve like this, okay, because everybody is rich. But if say people living in Pindi and Islamabad, okay, so it's definitely going to be flattened out. Okay, yeah, it's still Gaussian, but because the poor people uh, living even on other people's money, and they are very filthy rich people who have a lot of money, but then there is some average as well. Okay, so average may also move that as the situation is getting worse. So we say the middle class is eroding, so it's something like this. So if middle class is doing well, so average is moving to this. And if middle class is increasing, okay, so it is this, that middle class is increasing, everybody is making more and more and more and more and more money, and this way everybody is rich. And this is absolutely ideal. Or it is socialism or communism, everybody has the same amount of money. But this is interesting that you see how the Gaussian distribution is and how it changes. So these are the formulas why it is Gaussian, because just 2 parameters can help you to just recreate the data, which is mu and sigma. And sigma is the spread, and it will tell that in how much spread 68.27% people are, and 2 sigma is 95 point and 99.73 point. And we have seen this, that Gaussian distribution, the baby's weight are Gaussianly distributed. We have seen that no matter what type of mother she is, still it is Gaussian, whether it's black woman or white woman or white. And then we have seen head and length are also Gaussianly distributed. And the other thing, this is distribution of pregnancy length, first and other. So people have really spent a lot of time learning about all these distributions, your intellect. Here, things start becoming a little difficult. Once you are taking 2 measurements, once you have 2 features, one feature is fine, it's Gaussianly distributed, and you say, no, my feature is weight and height. Once you say my feature is weight and height, so they are related. The people who are tall will weight more, okay? So will weight more definitely because they are tall. So now comes another element in this, which is the cross correlation. So it is mu and sigma of height. Every people would have a distribution. And for weight, every people will have a distribution. So what happens is that here for the height, you have a distribution, which is Gaussian. And for the weight, you have scalar distribution, which is Gaussian. So this is very simple. But then these are not independent. You cannot have like a person who weight more is independent. He may be a small in height. No, there is a relationship, and that's why this distribution will tilt. Once you plot it in 2 dimensions, will tilt towards if there is a relationship between them. And the relationship, as we know, is that if you are tall, you are going to have more weight. Okay. So and this is the real data from newborn babies' weight and height. So it's also like this. The tall babies will have weight more, and so similarly. And now here becomes an example which will tell you that why it is the problem becomes very, very complex problem to solve. For this is a phase somebody has studied, and this is a paper. I have given you a link as well, and they are trying to make that who looks beautiful very subjective, very I call it quantitative. That okay, if these are the ratios, and you can say space, proportions, nose, this and that. But other than that, these all are Gaussianly distributed. Okay, the size of the nose, the width of the nose. There is a relationship between them. And so the nose with eyes and eyes with the your forehead. So you find out that though these are Gaussianly distributed, so all these measurements are Gaussianly distributed. 10 of these measurements are Gaussianly distributed. Uh, the width of the face is Gaussianly distributed. But width is related to the length of the face as well. Okay, you cannot have somebody whose width of the face is very rare. So though they will be Gaussian, every of these parameters is Gaussian, but then there is a relationship of each with every other measurement that you are taking, and that makes the modeling very difficult. And this is where you have to not only find out the means and averages, but you also need to find out something which is called the covariance matrix. And remember, we discussed about the covariance matrix in dimensionality reduction as well. That you first find out the covariance matrix, and then you take it to the PCA, which is the principal component analysis, to reduce data. So those parameters which are changing with the same proportion, so they are not adding any value for you to classify. They may be adding value, but not to classify. Or if they are just constant, again, there is no spread, then they are not adding any value because they're constant for everything else. So, but then is here, which is this thing, which is for the reading one, which is perhaps uh, your width of the face, for example. So its spread, you need to find out that in the population where you have taken the study, so what is the maximum, minimum, average, how does mu and sigma are for the face but then ये कोई हमारे off करने से. And then but then the one has a relationship with two. Okay, so one has a relationship with two. One is this from nose to your, so one is this, so one has to have some relationship with, there is d0 as well, so 0 has some relationship with 1, and 1 has some relationship with 2, 2 has some relationship with 3, and that are to be figured out, which if you have all these measurements, perhaps you can. Okay, if you have a lot of faces and you can detect all these points which are putting in red, or you make somebody to sit and just put all these annotations, and then you have some algorithms to take all these readings, and then you can actually plot all of them together, and then you can also see their interrelationship as well, that how they actually, but changing these would change the face, and this is generative AI as well. Changing these a little, remaining in that distribution, you can start generating the new faces. But you got to remain in that distribution. You cannot just make a nose which is the highest in length and then you don't change other things. Definitely, it will not make somebody look like a human. Okay? So got to remain in that. That's why learning the probability distribution is very important. That if you learn the probability distribution and you remain in that distribution, you create new samples. And that is what the generative AI is. So this is important, that every reading, usually once you say a model means that they may have many probability distributions, and those probability distributions may relate to other probability distributions as well. So you have this cumulative probability distributions, which only a very high computation, at very high computational cost, you can make the neural network to learn those distributions. Okay, this is what people have been trying in this generative AI. Okay, so the formula changes, and people say this is very complex to find the inverse of the, if you have a model like this where you say everything is Gaussian, okay, yes, everything is Gaussian, but finding the covariance matrix and its inverse is very difficult, and you don't know what is this, what the size is going to be. If like there are 1000 by 1000 pixels, and every pixel you say is a Gaussianly distributed, and every pixel relates to other pixels, for example. So you can just imagine that how complex this model is going to be. So people don't attempt to extract that model using the formulas. They let the neural network to find it for you. Okay, so that's why this generative AI is important, and which is about let the neural network extract some model for you, and then you generate the new samples. Okay, and we keep spending time, but today we'll spend little time on generative adversarial network because it relates to what we have studied as probability distributions. So what is an encoder? So, variational autoencoder is in many neural networks, and so we'll be exclusively spending more time on neural networks. But some of the neural networks, once you feed in an image, like is here. So this is an image you feed in. Okay, it goes through many convolutional layers, and you keep decimating, keep reducing the size of the image until you have the smallest dimensional image. Smallest dimension, but it has a lot of information in it. Okay, so the image starts high resolution, it's going smaller, 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 and it gets to the smallest image that you have. And this is where you flatten, because this smallest image has the information which you want the neural network to do. If it's a classification problem, it will say this is a bus, this is a truck, this is a motorbike. It will basically collect in that smallest piece of information, would able to help you to classify. If it is a segmentation problem, it will have the information, this is sky, this is ground, this is grass. Okay, so the image is going to basically, and this is the most synthesized, most informative piece of information, which is here. And as for example, here in the segmentation problem, from here, you basically do the interpolation through the neural networks and do the scene classification. Okay, so the scene classification is here. As you can see, it is taking an image, encoding it into a smallest piece, and then it is expanding it back to the same size. But now, because the neural network is not interested in doing the high resolution, it is only interested in figuring out where the road is, where there is a turn, where there's a traffic light, where there is a tree. So it just basically pasted with the same color. So it is every pixel which is otherwise is a red. Remember, a pixel, I told you, it is red RGB. So it is a red and a green and a blue, and 2 raised to the power 8 into 3. So those many possibilities for each pixel. But you say, no, 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 I want only every pixel to be painted like either a sky or a building or a pole or a, so you want every pixel to be just one of these colors. So you have reduced now the size from so many uh, different possibilities into only 8 or 9 or 10 possibilities. So, but this is what all autonomous driving vehicles would require. They don't need detail. They only want that, yeah, this is where I can drive. So this is the encoding. So, and I always say that generative AI is really very dangerous in this perspective, that you don't need any annotated data. That is the main charm why it has just taken over the world, because you don't need any prior knowledge to have a generative model. No prior knowledge. Otherwise, if you are doing research on cancers, you got to have all the CT scans, all the MRIs. Somebody has to sit down and precisely identify that which pixel of this MRI is malignant, or so got to do a lot of annotation, and that's so expensive to have. And also it depends upon the knowledge and the intellect of that person who is actually saying, yes, this is, and you need to have an expert doing this, okay? And in Pakistan, that's why you don't find any data where you can have that type of annotation, which can help you to train the network to find out whether a particular MRI has cancer or not. But generative AI does not require this. This is an unsupervised. That's why, as I'm saying, it is dangerous because it can learn by itself. How that? So, for example, you want to make this a generative so that it can just generate different things and learn the distribution. Now, generative AI whole objective is that all the data you feed in, it would figure out the distribution. Okay, how each pixel is related to the others, and so the hidden distributions it will figure out. So, and how you find out the distribution, you give is an image here from your database, and you give, and you have the same, you wanted to recreate the same. This is how you start. You take an image, you don't care what it is. Okay, you say, go through this network and recreate me the same image. And now you can easily compare, because how you compare every pixel of this minus every pixel of this, and you square it and sum it, that is the error. No, you have not created right. Change your weights, please. Change your weights, please. Okay. These are all the weights. So millions of these weights, change them and do it again, 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 do it again. Now you are close. Now let me change the image. And then everything is disturbed. You say, oh, again, do the change the weights, and you run all the data set you have multiple times, and ultimately you come to a compromise where you say, oh yes, they have learned the underneath distribution. Okay, and you don't want it to figure out what it is because you don't know what it is. Okay, you don't want to say this is 2 because you have to again make somebody to sit there and say this is 2, this is 1, this is 3. You are not in generative AI, you are not interested in classifying that this is 2, this is 3, this is 4, this is 5. Okay, you are interested in finding out the hidden probability distributions so that you can create new data, or you can find out that something is anomalous, something is not out of this distribution. So they are using it to find out, for example, cyber attacks. Okay, anything that happens in the driving car, something which is not in the distribution, because it has learned the distribution which it sees. Now, an aircraft is coming down on the road, they say, oh, there is something new, it is not in my distribution, so do something. Okay, so they can find out the anomalous behavior of something which is out of the distribution. They say there is something wrong, this is not even in my distribution. Okay? A baby born with 1 pound, we say it's not in my distribution, there is something wrong with the data because I have learned the distribution by heart. So anything which is not in the distribution, you can figure it out. And another thing which I'll show you is that it can help you to generate more data to do the better classification, because it's so difficult to generate data. Right? So many people are using it. So I was just helping somebody I know. He was doing his PhD from Georgia Tech, and he has only limited number of ECGs. So he generated so many more from that set because he made this to learn, and then once you make it to learn, then you say generate more, and then you can basically train your classifier. Okay, so this is the whole thing, that you have an image here. Sorry, so you have an image here, and same thing you put in here. And then what you do is, these are all the weights, and we are going to learn more about this, but these are the neurons connected with each other, and millions of them, or maybe convolutional neural networks. And this is the most refined information, which is the encoder. This is where you have encoded this into this vector, okay? And this is called the latent space representation. Latent space is the hidden measurements that you perhaps directly cannot measure, like temperature on the sun. Okay, there is no direct way to put some sensor and find out. You have to indirectly somehow find out that perhaps because this is the heat, this is the channel, so perhaps this is the temperature at the center of the earth, okay, or center of the even sun. So anything which you cannot directly measure, for example, you cannot measure emotions, directly measure. So there may be some measurement, but you cannot directly. So it's a latent variable, happiness.
But you can say, I can figure out somebody is laughing, and somebody may not be laughing, still may be happy. So it's a latent variable. So anything which you cannot directly measure is a latent variable, which is hidden. And this is what it is trying to figure out, that Z is the latent variable. It says, I can figure out the main thing in this data. So this is the magic I can do. Okay. So because now I have the latent variable, so I know what it is. And with this, I can recreate the same thing, which I'm not interested because I already have 2 here. Why would I like 2 to be recreated? There's absolutely no point in just creating something which I already know. Okay. So this whole point is that now I learn this data by heart, and now you can ask me to, as I am saying, something which is not in this data. I can find out anomalies, or I can create like new things, new faces, new data, and that is what the generative AI. So simple that you have X and you have X hat. X hat is here, X is here. So you have the original data, and you have the recreated data, and you find out this squares. This is where every pixel is to be subtracted, square, and added to find out the loss. So loss is important
in AI, that this is a loss function. If you can make it 0, means you can exactly creating this, but you will never ever able to make it to 0 in most of the cases, but you can reduce it. So the job of this is adjusting these weights is that you try to reduce it as little, as small as possible. So just keep changing the weights. What are the things that you can change? There are the weights. I'll show you a picture of that as well, and that you can change. But this, in experimentation, we say that if there is 100 samples, so then we can say that the results which we are getting, they are close to the true situation. So when generative modeling is creating these samples, so do we have anything like the number of benchmarks or samples which are required to create the samples? Yeah, that's what we are going to learn, that what are the benchmark that will help you to generate new samples. Okay, but here this is important. Z is important. Okay, Z is like encoders have been there, throughout the history of communication. Like the picture you take is JPEG encoded. Okay, the video we are recording is MPEG encoded. Okay, so encoding has been there. The once you zip a file, it is so, but encoding has been only to reduce the amount of information or to gain something while you are transmitting. So encoding has never been to recreate something which is new. So here this encoding is that you are trying to find out the essence of the data, and that's why you call it, you want to find the latent space of that data. Get into the latent space, and then we'll show you very, very interesting things. So these are the weights. So this is what are you trying to do? For example, here is this 28 by 28, 28 by 28 pixel image. Okay, if you're not using convolutional neural network, just you're using simple networks. So every pixel goes as an input. Okay, every pixel goes as an input. So how many inputs are going to be there? 20, 28 by 28. These are the number of inputs. And then you have many hidden layers. So every this input gets multiplied by a number, by a number, by a number, and every input is multiplied by a number. And you add and you put some nonlinearity, which we will learn. Okay, so you have one layer. Then again, every input gets multiplied with a number and gets added. And how many nodes should be there? And people have done, so they are established models. You can just copy that model here. You don't have to do the experimentation, creating your own neural network. So there are like something already there out there, and you say, I'm going to use this one, I'm going to use this one, and you can always retrain their weights if you want to. Okay, there's something called transfer learning, so you can basically make it learn on the new data that you have. For example, this neural network is only to classify fruits, and you want to now classify some other objects. So you say, I'm going to use the same network, but I'll do the transfer learning, and now I'll retrain it on this. And how many layers you retrain, because these are all the layers, and you say only layer this, because all these layers we will find out are without you worrying extracting some features from that image. Okay, And this is the latent variable. And now see this amazing that it is only two numbers. The two numbers can basically create and clean this, all these numbers, two numbers only. So two numbers are controlling that what you create. Okay. And so two numbers are the smallest piece of information. And you say my latent space is these two numbers, along with the weights. But there's a lot of baggage here, a lot of baggage here. Okay. So once we have modeled it, you throw this away. You say, I no more need this. Okay. I have these two numbers, and with changing these two numbers, I can recreate everything which is there in the database. Okay. And more than that, I can create something which is not even in the database. We'll see how that happens. So what they have done is, this is these autoencoders, variational autoencoders. So this is autoencoders. This is a vector. Okay, just one vector for whatever you feed in is going to get through this, and you are going to get a vector here, which is your latent variable, and it will be a fixed vector for every image because it's coming through the weights, and you get a vector, and then you pass it to the decoder and you recreate this image. But in order to create, they made it this z into a probability distribution. Every z variable is Gaussianly distributed. Okay, so every z has a distribution which has some mu and some sigma, every variable. Let's say if z has 10 numbers in it, so there are 10 distributions in it. Okay, so this latent variable is no more latent variable, it's a latent space, and every variable has its own distribution. 10 distributions, everything has a mean and a standard deviation. Here, these are only 10 numbers which are specific to an image. Through this training, they try to find out mu and sigma for every z. Okay. So if they do this, this become variational autoencoder. Why variational? Now you can have a sample from, let's say you just have a variable z naught, first variable, z1 is second variable, you have z10 is, these are 10 numbers. In case of autoencoder, every image will have these 10 numbers. Okay. In case of variational autoencoders, this will have, a number will have an average value and a sigma. Okay. So you will have a distribution, and you may even have like how they relate to each other as well. Now what you do is that instead of just creating something which is average, you change the value of z here. Once you change the value of z, you create something new. Okay? And they have actually learned that what every z is doing to your image, that is even more interesting. Okay, for example. Okay, so these are all the faces they have fed into this finding out z. And because it's all fair faces, so they said the good is that you have all kind of faces, all kind of hair, the black people, and the male and female, the aged, and because you want the distribution to learn the entire population, so that once you create something new, it is just creating not always white people, but it is just creating anything which is out of in this distribution. So you make it learn the distribution. And now look at this. They say there is one variable z which makes you smile. You change it. Once you change it, this is a serious looking guy, and the same. Now he's laughing. One variable, make any image, smile. You just change that z a little. Keep rest of all the numbers same. The image will start smiling. Okay? And this is where you wanted to tilt his head from left to right. Okay? Here, this is looking right, and this guy is looking left. Okay? So you can tilt the face by changing. So they realize that every number is doing something to your image. And you can learn it by only changing that a little, and then find out what it is doing. Okay? And then you can have another way to control that what you intend to generate. Okay, so that's how people are using generative AI to generate. Let me first show you that, then we'll come back to these. Look at this. This changing a little. This age here, now he's going to become a woman, and women. So you can just change the changing these. You would just able to change the this image, and you'll able to make something which is even more interesting, So this is what this handling the latent space would actually help you to control what new you want to generate out of this. So let me show you this up, then I'll come back to. Okay, so here is the, for example, this is the latent space. This is the latent variable z. Okay, now you're changing something, moving from one point in the space to another point, and you started with this bird, and you have totally a different bird. And you can see the transition as well, that how this bird looking right is now looking left, and totally a new bird, which perhaps does not even exist in this world. So by having this Z, you can just change, it is the same the case in production, that you're producing something interesting and you have this grip on the latent variables. So people started figuring out so many interesting things out of uh, generative AI, that you have this handle on this latent space and latent variable, and play with this latent variable, and then they're just trying to make sure that if you live within the distribution, you always create something which is meaningful. Okay, and they make sure that all these distributions are connected to each other. There's no gap. If there is a gap, you may just able to create something which does not really make sense. So there are ways we'll get into more of this, but
So can we say that because in a given word, is a word mutation? So a little change
can change you. Yeah, perhaps in one way, but this primarily is just the distribution that they have learned, kind of. Okay, so I have generated some code, and I'll also give you an exercise to work, because interestingly, your chat GPT can also generate you the code which you can use to have these networks, and you can have your own specific problem that you want your generative AI engine to learn. Okay, so these are, so now people started like focusing more on this after variational autoencoders. They said, why not to have generative adversarial network. आपने wait करना है? Change. Okay.
you can be asked chat GPT to generate another chat GPT which is smarter.
नहीं, I don't think so. The reason is, Zahra, they have their own controls. Actually, the Stanford University, what they did was, once they have this model, okay, they Llama came, Llama 2, and they said, okay, you can fine tune it. Okay, so what they did, they gave like some data to ChatGPT and asked it to generate more of this. So generated humongous amount of data, and use that to fine tune the Llama 2. Okay, but obviously ChatGPT did not like it. That they actually, a competition basically used ChatGPT to create something which people think that may, just which may take over the ChatGPT itself. So things like that you can do. Like you can generate more data for a specific type of data. For example, you are working in like we have developed a new office system. So I'm very interested in developing um, uh, a generative AI to attach with the office automation system, where it can just generate all the letters, memos, but I don't have humongous amount of data to train. But what I can do is I can give it to ChatGPT and say generate 10,000 letters, which are just kind of like this. Okay? So it'll generate all those letters, knowing whatever knowledge it has, and then I use it to fine tune the model that I'm trying to fine tune. So these are the kind of things like people are doing. So So GAN is a very simple idea again. Generative adversarial networks is a very simple idea. And this is what I told you, that what people are doing is that they are using a GAN model to generate more data and then feeding it to the classifier. For example, this is the paper. Here is the link as well. So you can go to the link and click and to find out the paper. But all it is doing is it has data for diabetic patient. For this is the data set 1019 Mexican nationals, and there they have 499 non-diabetic, which we call controls, and they have 520 diabetic, and they have very less amount of data to train a deep neural network. So what they did was they said we use GAN to generate more of this data. And what is the data? This is interesting. Now you will understand the thing that I've been just trying to convey. Like, you find out that there are like parameters like age, gender, education, weight, height, waist, hip parameter, BMI, WHR, SBP, DBM, glucose, MMO glucose, insulin, HOMA. Okay? So all these are the parameters. Okay, and you have these parameters for 1,000 people, 1,000 patients, and you know that these parameters are for the diabetic patients and these parameters are for the non-diabetic patients. Okay, and so means that you can find out the distribution for the age, which is definitely going to be Gaussian. Okay, you say, oh yeah, this distribution is like this. So most of the people who have diabetic is age 42, for example. But you can still find very few which have age 18 and they are also diabetic. Okay, or it may have some other distribution like this. Okay, but or they, you can say people who are diagnosed with diabetic 42, but you say a person who is 70 years old and he is not diabetic, so perhaps he will not be diagnosed for diabetics at this age. So genders you will find out almost the same. And then there are other weights, and you say weights is also Gaussianly distributed, and height. And but then you realize that they are already related, weight and height. Okay, but you find out perhaps weight is also the fat people. They may have level of glucose in the blood is more. They are more correlated. Okay, so this is what the once you have this data and you're finding the covariance, which you can easily find because it's just a table, and you say find out the covariance. I'll just give you covariance, and you say okay, now I have the covariance, and you can just give it to PCA, and you say just reduce the size and give it to classifier. It'll just classify. And then once you have new patients coming in, you find out that it's still making errors because perhaps the data was not enough to exactly figure out that who should be labeled as a diabetic patient and who must not be labeled as diabetic patient. So you need to have more data, and you want somebody to learn the distributions. Out of this data, learn the distributions. And this is where you say, let's GAN learn the distributions for all this, and let GAN to generate more data. Okay. So, but this is a one-dimensional data. This is important. This is one-dimensional data. So, so I asked Chat GPT to just create some data and try to learn the distribution. Okay, and I'll give you the code, and because you yourself will be just doing this, it's a very interesting exercise that you do, and you see that how it start learning. Okay, and this is ultimately, this is the real data that the distribution. This is the generated data which it has tried to learn. Okay, in whatever little capacity it could. That's what it has learned. So how the GAN works is interesting, as I told you earlier. It is like you have this latent variable, but you make this latent variable as Gaussian noise. Okay, as Gaussian, you start from here. You say, I'll feed in some noise, and this is the network which I showed you earlier. Okay, it's a neural network where there are multiple layers, and all those layers are actually generating. Remember, the generator is this. Yeah. So generator takes the small amount of information and expand it to an image. Few parameters, which is in the latent space, few parameters, and it makes it into an image. This is the generator. And this is the encoder, which basically helps you to find out the distribution of Z. Okay. So we are talking about a generator, which is going to take Z and out of Z, it is going to. So this is one way of generating Z. One way is variational autoencoders, where you have something here and you have the same thing here. And if they are not matching, you try to basically adjust the weights, and to find out this distribution. Right? This is one way. And other way is interesting, which is this way. Okay, in this way, what you do is you say, I will just start from noise. And obviously, what I generate is going to be garbage. It'll be just fake data. It'll look like this thing, which is very fake. For example, the problem I was trying to solve, the first thing it generated was this. Okay, I wanted it to generate this. It generated this. And even after 100 epochs, after 100 passes, this is what it has generated. Obviously, there is no match because I'm just making it to do from the scratch. Okay, from the noise, I wanted to generate this. Okay, and how it can do that? Now, this is a question. So you have, so you generate a fake data, but you have the real data as well. Okay? Now you have another network, which is a discriminator, which knows that how a real data looks like, because you feed in a real data and you tell it, this is real data, learn please. And you do several passes to make sure that it learn what real data is. Okay. And now you pass this, tell me whether it is real or not. It's definitely going to say it is not real. It says 0, it is not real. It does not even look closer to real. So it is like, this guy is like say, if you want to print fake currency, okay, a fake currency, you are printing, you have a printing press, and you are saying, I'm going to print 5,000 note, fake note. Okay, but because I don't know the detail, I'm going to find out a friend, a conspirator, or a person who works for State Bank and who is specialized in figuring out the fake notes. Okay, you make him a partner. You say, I'll print, I'll bring it to you. Okay, you will tell me what is wrong with this printing. You say, no, there is a line, you know, there's something written here. We have put a dot here. And I'll go back and I'll change my printing and I'll fix it. I'll again bring it to you. Okay. So I keep doing this, keep doing this until you say, oh, I cannot figure out of these which one is fake. Okay. And once you come to that level, you say, now I have the model. Okay. So that's how this thing works, that it just generates some fake data. A discriminator is trained to know that this is real. And it said, no, this is fake. This is fake. You go back, you adjust the weights, come back, adjust the weights, come back, adjust the weights. A time comes once your discriminator says, I really cannot figure out which one is real, which one is, because you're feeding real, you're feeding fake, real and fake, right? So that's the simple way that GAN works, okay? And if you ask the ChatGPT to generate a model, it'll just generate a model for you, that for the discriminator and for the generator. So there are two parts, a generator part and a discriminator part. So for example, you want it to learn like some distribution, you have some data distribution, and you say generate fake data. So mostly, let's say it has generated this fake data. This is the generator which is generating the fake data. You say generate 64 samples, it'll generate 64 samples, okay? And then you ask discriminator. Discriminator knows that here is the distribution. This is where the data should be. All those 11, 12 parameters, these are the distribution. And but because the generator does not know, so it has no way of knowing where actually the distribution is. So the discriminator is going to say, oh, you are fake. The data is fake. Okay, this data is fake, completely fake. So it says this is the probability of this data to be real. Okay, and it improves itself as well. It says, oh, this data has to be real. So I feed this as an error to adjust my weight so that I say with probability 1 that this is real. And I make them 0, so my model should say this is fake. So it says, let me change feed in that this should be 0. It is fake data. I must not say that this is even real probability of this to be a real, because it's a fake data. I know, because you're telling me, hey, this is fake data. Okay. So, but this is real data. I want this to be loud and clear that this is real data with probability 1. So, okay. So you train the weights and you say, okay, this is fake, this is real. Now what the generator is going to do is it's going to make another attempt, another attempt, another attempt, another attempt. It's going to make another attempt and start getting into the distribution. Slowly but surely start getting into the distribution by the weights it is adjusting, and increasing the probability that it start looking like a real data. And then you go and then you find out it gets into your distribution. Okay, because now it is in your distribution, it will be very difficult for any discriminator to say which one is real, which one is fake, because it learned the distribution. It says, oh, this look like a real data. Okay, so you learn this, and then you basically have the model. You have a generator and a discriminator, and generator would learn to basically generate something fake which looks like real. Okay, and that is something that we have seen. So these are called GANs. Okay, so here are the samples of real faces. Here is the random noise. These are all the weights that you are training, and the generator. And generator, you give it, and this is the discriminator, which has only 2 output, whether it is real or it is fake. Okay, so it's just doing the discrimination. It has only have to say true or false, true or false. Okay, and you put this generator generated phase, and you tell it it is false. Okay, you tell this it is false actually. Okay, and then you put this and you tell it it is real. Okay, but it has to have only one set of weights, and then it starts getting confused. It says, oh, they are the same. Okay, so both are just so real that I cannot distinguish. And you say, okay, I have trained the model. I have a generator which basically is generating the faces. Okay, so this is where you have both of these, and you G tries to synthesize fake instances that fool D. So पूरी कोशिश है somehow with the help of the discriminator. As I said, now you have in partner in your crime is the person who actually figures out whether this note is a fake note or not. Because you have him as a partner, he has helped you to print something which looks so real, because you have that person which has all the knowledge of that this is real, this is fake. Okay, so you have this, and you reach to so this is loss function training, and then now you have just the generator. Okay, now you have a generator whereby changing this Z, moving in the space. Okay, you move in the space, creating new elements. Okay, something which is fake but looks very like real. Okay, let's wait for the answer. So does once you ask it to write a letter, so it is freakishly generating something which is not there. Okay, it looks like real. You say, write this letter, like this poem, make this painting, do this or that. So it just because though through different algorithms, but it has also learned to generate something new which looks like real. Okay, and so you generate all these things, but just by prompting the chat GPT to do that. So this is again now.
So in this case, the real data was done, but he is
Yes.
converting it to a
Yes.
real, like look like
A real bird which does not exist.
So how this would be differentiated that this is not
A real thing?
Yes, sir.
Yeah, because it is usually what you are generating, and you are moving in the latent space Z, and it is usually not one of the samples that you have in your database. Okay, so you have learned it. So you have all these real images. So at least it is not one of the thing which is there in the real images. Okay, it is not one of those things.
In this generative, we needed to have such like thing which we are actually giving something that is new but not giving anything else.
Yeah, mostly because in this case, because as it has learned the distributions and is just having any sample point and regenerating something which looks like a bird, freakishly look like a bird, with kind of the same distributions, which even the discriminator cannot figure out it's a real bird, or it really does not exist in this bird because it has also learned through all these images which we have fed in. So it may look like a real bird, but for sure it is going to be something new, as all these people. Okay, so all these people, as you can see, just changing a little in Z, you are just making a man into a woman and changing the age and looks and everything by just having a control on the Z. And so most of the remember I showed you the website which says this person does not exist.com. Okay, so it uses GANs as well. Okay, so it uses what we have learned today. So if you go on this website and you say this person does not exist.com. Okay, so all these are GAN. So whenever you click on this, it'll generate a new person. Okay, and you may argue this person may be existing, but it does not exist in the data. It's just changing that latent variable Z through the GAN. It is just generating all these. So as you can see, there may be something where there were two pictures, but all these are just faces. So amazingly look like real people. Okay, but so there is something like epochs, and so what I have done is, like, here is I asked ChatGPT to we'll come to this at some point. This is what I wrote to ChatGPT. ChatGPT, generate Python code for implementing a generative adversarial network to learn a distribution from 1D sample data and generate new samples from the learned distribution. It has not generated the same data. It has generated a distribution which looks like, or with perhaps a discriminator. This discriminator could not figure out. Okay, so and it asks that you can give it some other data as well. So it will generate something new, which the discriminator will fail to figure out that it's a distribution. And so this is the code. Okay, after a few iterations, I was giving a little error, but I kept feeding the error to the chat GPT. And in maybe in 2-3 minutes, I had this whole thing working. And as you can see, it is generating real data, batch size, and the real data batch size is 64. So it's just generating. You need not to really know Python, but if you even read it, so there is a generating in real data. This is a generator. This is the discriminator. So you have a generator model and a discriminator module. And then it just does all of this, and then it has using that. So this is what it has generated. Another distribution, which is not the distribution which looks in blue. It is something new data.
चलो यार
Okay.
अब तुम इसको ऑन करो ये ऑन कर दिया
Let's go off. Okay, so, and this is how it started. So after passing 164 those 100 times the 64 numbers, now it is just adjusting the weights and weights and weights, and I see it like coming closer. It's after 300 epochs, seeing the network seeing the same amount of data 300 times, and 400, 800. Okay, so this 10,000. Okay, so it has started generating something which looks like, at least discriminator has not figured out that this is a new data. It says, yeah, it looks like something which is new. So this is important. Like, the GANs are to basically do this, that you make it to learn, and for many applications, for something, if you want to generate new things, it is primarily in design, in fashion design. People are trying to generate new clothes, new bags, new products. by just, and then they have, you know, so many advancement even in this, that that you can do a hand sketch drawings and give it to the GAN, and it'll just try to make something which looks like what you have drawn with the hand. And so it's just a whole new area, and that's what I've seen in GITEX as well. So everybody's talking about GANs and generative AI, and so this is the new excitement in technology. That so, but underneath probability distributions, learning about those distributions, and so I want to cover this. Let's just start it, and then stochastic processes as well. And I have a good use case in this. So we know random variables. We said there are like events. The sample space has events, as I gave you an example of people coming to vote, and the sample space is where they vote. Sorry. So this is a sample space, and it has all the possible outcomes of something that you are studying, all the possible outcome. If it is a hospital, if it is a class you are taking, all the possible grades. So we call this a sample space. So every outcome has, and you can find out by collecting data that every outcome has some frequency of occurrences, and that with that frequency of occurrences you can find out the probability. The random variable says that because these are the names PTI, PPP, let's say that this is your sample space for the elections. A person can come and vote for Jamaat-e-Islami or PTI or Muslim League Noon or PPP and all others. And you think all others is I have just one event, and if it is not out of these, so I'll put, but you have covered the entire sample space, okay? And you say, I will say, and for reason you may just have some reason leftist and rightist, as I was mentioning, so that once you get a mu, so you know that it is tilting towards left or right, the people are tilting towards left or towards right. So you say these are your so the sample space mapped onto real axis, it becomes a random variable. So random variable x can have a value of 0 if somebody has voted for Jamaat-e-Islami. Random variable can have value of 1, like a variable, if somebody has voted for PTI. Random variable has value of 2 if somebody. And everything at the end of the experiment, end of the election, is going to have a probability. Okay. From last elections, you may have all these probabilities. For every polling station, you can have all these numbers. You can figure all these numbers out. And so, and then you say, okay, this is perhaps it's totally non-political. Don't go on these numbers. It's nothing to do with my personal preference. But, you know, let's say that you say perhaps half of the people are going to vote for PTI and 1/4 for Muslim League Noon and 1/4 for PPP, and very little to others and Jamaat Islami, for example. So these are the probabilities that you get after an experimentation, or you may have belief, or you may have some sample polls that you say, okay, perhaps this is the it looks like, and it may change from constituency to constituency, from polling booth to polling booth, from a house to every house. It depends what is your sample space. Uh, so what is a stochastic process? These are the random variables. Okay, those are the random variables, and then there's a random process which has to do something with our real life. Random process is different from random variable. This is a random process. It says a stochastic process or a random process is a collection of random variable indexed by time. This is important. It's a collection of random variables indexed by time. And how do we see this? Here is now your sample space. This is your sample space, has certain readings that you are taking, but now they are time series. For example, temperature of a day. Okay, and you start noting temperature of a day, which is kind of a continuous variable, but you can take only values at every 2 minutes or 5 minutes. You go, you take a value, you take a value, you take a value. So it becomes a stochastic process, because next day, once you're going to take the temperature of the day, it is going to be different from what it was on Monday. So it may be on Monday, but Tuesday you see there is a variation, and Wednesday again you see a variation. Okay. So it's that simple, that because they are not fixed, so just 1-2 minutes will take. So every day, and I'll give you an example here where, for example, number of cars crossing the gate, or number of cars entering into the gate in every 5 minutes. Okay, you say from 000 hours to 2400 hours. It's changing. You say no car, no car, no car. 8 o'clock, you start seeing cars, 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 and then it's increasing. At 12 again, going down, down, down. It's a 0. Okay. Next day again, you run this experiment, and you say number of cars entering every 5 minutes. You keep collecting, and now you want to find out that at 9 o'clock, how many cars enter into B70. Okay, or you can say from 9 to 9:30, how many cars enter. Okay, so from 9 to 9:30, then you say, okay, and you find out it's a Gaussian distribution. That is a random variable. Once you fix index as a time, you say at this time, this value, this value, this value, you put it in a vector, and this becomes the possible outcome in the sample space, and this is your random variable, indexed by time. You change the time, you say number of cars entering at 10 o'clock. Okay, so it'll change, every day will change, again will be a vector. So a random process is a process where you run an experiment. Experiment is a time series sequence. So this becomes very important in our life. Mostly we are dealing with this. Okay, number of people entering in a restaurant, if there are patients, his temperature, his blood pressure, his everyday. Okay, and so understanding the stochastic processes is important to do the planning and decision making in many cases, and we'll see an application. So let's wait for 30 minutes and then we meet again.
डेटा हो, जैसे हमने डिफरेंट हार्वेस्ट फ्रूट्स हार्वेस्ट का डेटा कलेक्ट किया हो, अप्रोक्सीमेटली हमारे पास 1000 सैंपल्स का डेटा हो, और लेकिन हम अपने जो हम मॉडल डिज़ाइन करना चाह रहे हैं, हम उसमें चाह रहे हैं कि ये मज़ीद प्रिसीजन हो, तो मज़ीद डेटा, तो क्या हम इस जनरेटर के थ्रू उस डेटा को और मज़ीद डेटा जनरेट करवा सकते हैं? और अगर जो हम जनरेट करवाते हैं वो कितना रिलायबल है, क्योंकि हम अगर हम आगे जाकर उसको किसी डिवाइस में जो कि उसकी इंटरनल डिजीज को डिटेक्ट कर सके, हमने उसमें जाके डालना है, तो वो कितना एक्यूरेट होगा? और दिस इज जस्ट फॉर रिसर्च पेपर, और या ये आगे जाकर मार्केटेबल भी हो सकता है इस तरह का मॉडल?
नहीं, बिल्कुल हो सकता है। देखिए, ये जो मैं आपको पेपर की भी बात कर रहा हूँ ना, इसने एग्जैक्टली यही किया कि इनके पास सिर्फ 1000 पेशेंट का डेटा था, ठीक है, और जिसमें नॉन डायबिटिक और डायबिटिक तकरीबन 50-50% थे। तो इन्होंने गैन से इसको ऑगमेंट किया, डेटा को, और डेटा जनरेट किया, ठीक है, और फिर इन्होंने ये साबित किया कि वाइल जनरेटिंग मोर डेटा, आपकी जो परफॉर्मेंस है किसी भी क्लासीफायर की, ठीक है, इन्होंने रैंडम फॉरेस्ट यूज़ किया हुआ है, विच वी आर गोइंग टू स्टडी के, तो उसकी परफॉर्मेंस इंप्रूव हो जाती है बिकॉज आपने नया डेटा जनरेट किया। तो आप ये जो एक और क्वेश्चन था कि हम गैन के ज़रिए और डेटा जनरेट करके देख सकते हैं, और जब आप उसको लेट से आपने स्प्लिट किया हुआ है 30-70 पे, जिस पे आपने इसकी वैलिडेशन करनी है, टेस्टिंग करनी है, तो देन यू कैन सी कि बिफोर you have generated the data and now once you have generated the data, how your model is performing. और अगर तो आपको लगता है कि तो बड़ा अच्छा परफॉर्म करने लग गया है, ठीक है ना, तो इसका मतलब ये है, तो बेसिकली ये क्या कर रहा है गैन, क्योंकि ये डिस्ट्रीब्यूशन जब सीख रहा है तो ये काइंड ऑफ इंटरपोलेशन कर रहा है ना, उसकी डिस्ट्रीब्यूशन निकाल रहा है पूरी। द मिसिंग डेटा जो सैम्पल्स हैं वो हैं विच इट इज़ नाउ कैपेबल ऑफ जनरेटिंग, ठीक है ना। तो अब क्योंकि इसने डिस्ट्रीब्यूशन सीख लिया, वो फॉर्मूला सीख लिया है, अगर वो इसने सही सीखा है तो वो डेफिनेटली विल हेल्प यू, नॉट ओनली फॉर पब्लिशिंग बट ऑल्सो इन अ फाइनल प्रोडक्ट। Okay.
Random process, as we have understood, it is the time series, and it may be temperature, pressure, your blood pressure, your number of people. Okay, so anything which is changing with time, and you are taking multiple readings, and then you index. So important is it is indexed by time. Okay, so otherwise random variable is x. So time becomes important. So once you change the time, you get another vector, another set of values. So that's why it shows the time is important. This is t1, t2. So you may have multiple ways to represent a stochastic process. So this is called a stochastic process. Right? So here is the experiment. So this may be the day, and this may be the time. Okay, the day that you are running the experiment, this is the time. So on this day, this is your readings. On this day, these are your readings. On this day, these are your readings. Okay, for a day it is just a signal, but once you fix the time, then you have to have that the time is fixed, and fix the time, and then for every of this random, every of this waveform, you get a value from here, value from here, value from here, value from here, and you put it in a vector. If it is a continuous, so continuously you can change the t, and every time you get a value. Okay, every time you get a vector. So this is where t usually is time, omega is your one of the experiment, one element, and so you can definitely fixing the t, you get a random variable. ठीक है, जिस हमने random variables पढ़ा हुआ है उनकी possible ये outcomes हैं, जिस हमने you may just want कि the people coming and voting for somebody, for example. तो उसमें आप different random variable may have different values. Every minute कर लें कि so her value, then you have a value, and x like person came voted for this, person came voted for this, and you say at this time you can make an array of numbers. And why these are important? For example, here I said कि जी मुझे ना आप एक generate करें as if there are temperature of the, for example, temperature of the day for first 100 days. Okay, so it goes from, let's say, midnight se leke the midnight of the next day. Just noting the temperature, variation after every 5 minutes, 10 minutes, taking reading. So this becomes one instance of a random variable. If you're doing every day, so then you can have a stochastic model to know what temperature is going to be at 12 a.m. or 12 p.m. every day by just looking at a random variable and its distribution. And mostly that will be spread like Gaussian, depending. But if you fix t, it becomes just a signal. We call this as just a deterministic time domain signal. Our interest is not in just one reading of this. Our interest is in the collection of it, so that we can do figure out the whole process. If you want to know the traffic on the road, okay, you want it to be a random process. Okay, you want to study it as a random process, because traffic is going to change every minute. Okay, at 9 o'clock it will be different, at school time it will be different. Okay, so how do you characterize a random process? You characterize this by mean, by autocorrelation, by cross correlation, by autocovariance, past frequency, some of these. Okay, so one is the mean. Let's say what is the mean of, for example, you say for 7 days I just want to know the mean temperature which is varying throughout the day, or the mean traffic is which goes on the road, or the traffic that enters in Islamabad. And so you can just plot it as a mean of traffic for all the days that you have collected. So the mean is also going to be a function of time, because it is changing. If it is the traffic that is entering Islamabad, and every minute that how many cars, for example, and you say I want a mean, so mean will show you something like this, and it will definitely is going to show you a trend. A mean is going to be a trend that the traffic is usually more on average at this time, and traffic is very less at this time. Okay, so you can find out by having the mean process. It'll give you some indication of the process, the mean. And then if you want higher level statistics, then you go for the autocorrelation and cross correlation as well. I'll give you an example. So this is the mean. So mean is where you say, okay, sometime traffic is very high, sometime it is low, sometime it is this, and you are plotting the mean, and mean is varying like this. And a lot of planning you can do by knowing what your mean is. Okay? But sometimes you also want that how this mean is spread. So you can also plot, maybe it's 1D standard deviation, 1D standard deviation, because you have way to find out it's just a vector. So you can find out it's, so this is the mean. Autocorrelation is primarily as at two different times you see how similar your pattern is at T1 and T2, because you think that the traffic or the, for example, the load, if you look at the electricity load, it looks something like this. So it is from almost 8 o'clock to 10 o'clock, it peaks. Everybody is going to office, school, so you are using a lot of electricity. Then there is a saddle. Almost in every country I have seen there's a saddle. And then it goes up again once you come back home from 6 o'clock to 8 o'clock. And usually in most of the countries, the minimum electricity usage is at 3 a.m. at night. So there is usually a pattern. So there is a correlation. So you can find this correlation by not only seeing it, but finding an Rx T1 and T2. So it's just going to vary the time and see the similarity in the, and wherever you find a higher value, it means they both are related to each other. They're correlated with each other. So this is, and covariance is like the same, but you subtract the mean of the two. But mostly we use autocorrelation and cross correlation. So this is the formula for autocorrelation. And what is the expected value? Mostly you, if you have a digital data and you want to see what the autocorrelation and the cross correlation is, this is an example which I thought of just showing you, and we can have an application built on this. This is, let's say, a PC hotel or a Serena hotel. Okay, and they basically are serving lunch and a high tea and a dinner. Okay, and they are interested in finding out that how many people come for lunch and at what hour of the day. Maybe resolution could be smaller or higher. I've said how many people are there 1 o'clock, and from 1 to 2 o'clock, and from 2 to 3 o'clock, and here they close their lunch, so they're no more serving lunch. And then for the high tea, they open high tea at 4. So all the people who entered once the high tea is open, and this is the last time they are serving high tea. And here just people are coming maybe for a cup of coffee and other stuff. But then their dinner starts at 8 p.m. until midnight. They are serving dinner, and still there are people who are coming maybe for a cup of coffee or for just, they are just living there or whatever. And they want to have a stochastic model. They want to understand more so that they can improve their business and run promotions or make decisions. And this could be good for any business, as a matter of fact. If you could stochastically model this, means it is good for any business. Right? So you say, I am going to collect this data, and which is already there actually, as a matter of fact, which is just there because they know they are billing everybody. So they kind of know that how many people every day they come. So your this is a random stochastic process, and every day, for depending upon how many number of days that you collect this data. And so you're collecting this data, and so you have all these days and the people number. And now, for example, you want to find out the distribution for the lunch, that how many people on average comes, and what is the distribution? Is it Gaussian? What is the standard deviation? How thin or thick? It is spread that they are not certain, or it is very certain. So it means that their spread is less. Right? Spread is less means you can do better planning. If spread is more, it means that you cannot do good planning, because if there are 2 people and 50 people, so there's a big spread. So, but if they are that there are 20 people or 30 people or 25 is the average, then you can do better planning. So that's what you do, that you have all of this data for all the days, and because you want to have a system where you are helping them to enhance their business, so you collect this data, and then you say, I am only interested, let's say, figuring out the distribution for lunch. So this is for lunch. Okay, so you add them up for all the days, the lunch time, how many people are coming to have the lunch, because they need to run, for example, their supply chain management, that how many people should they expect. And this is, let's say, for high tea. And this is for dinner. So dinner, high tea, and lunch. And every day, there are number of people. So this is all the stochastic process, and you have cumulative it so that you only want to see for these three timings, okay? Because you are more concerned about the lunch time, the IT time, and the dinner time. So you have this, and then you find out that they all are Gaussianly distributed. Like for lunch, you say there are 200 people on average they come, and their two standard deviation away is 230, and here is 180, for example, 170. Okay, so this is where they say about 98% of the time, this is what they are going to see. Okay, so similarly for the high T, they say, okay, this is now you're doing the analytics on the stochastic process, and you have these three timings, and you have now stochastically, you have a better visibility. Just showing one screen, this is what it says. So you have this. Then you want to find out correlation of different timings of this variable. You say, okay, I want to see that how lunch and dinner are correlated with each other. Are there any correlation between them two? Like if more people are coming for lunch a day, so I see the same trend for the dinner as well. Maybe it is Saturday or maybe it is Sunday. Okay, so you want to see that pattern as well. Then maybe Sunday, or it is Saturday, or it is so you can do the, and you can maybe can do it with another random process, which may be the traffic on the road, maybe. Okay? And you say there may be some correlation with that, and you can have a cross correlation as well with some other thing to check whether these things are correlated or not. So T1 and T2 means that you have one line you draw here. Yeah. So here, one line you draw at this is your T1, and one line you draw here, this is your T2. Okay. So your X of T1 is, if it is for 100 days, for 100 days, the number of people coming. So it is a 100 element array. And XT2 is also a 100 element array. And similarly, XT3 may also be if you want to see the high tea and dinner and lunch. So because these are the timings where you are interested in finding out their relationship with each other. So you can find out by having the formula. So I asked ChatGPT to generate this data for me, and I wanted it to plot the time series data as well. I prefer a stamp plot instead of plot. All values of the data should be non-zero. Keep the average to 30. So I'm just trying to see how the autocorrelation or how's the data looks like. So this is the ChatGPT has generated the data. This is for, let's say, a T1. This is the data for the lunch. Okay, so this is XT1 and index with time, and this is the same data. It's a histogram that it has plotted as a distribution, as a probability distribution. That what is the probability of having these many people, and this is the auto correlation. What auto correlation does is, let's say you have a data where you have Sunday and Saturday and Sunday more people coming in, and then you have on average Monday, Tuesday, Wednesday, Thursday, Friday, and then again you see more people coming in. Then again you have like 5 days of the week. Then again you see more people coming in. If you autocorrelate them, you will find a pattern, a cyclic pattern. That there is a pattern where every 7th day or 6th and 7th day, there are more people. So once you do autocorrelation, you run the signal on itself. And you see that once you run it, so there is definitely going to be high value once they are just, you start and once you keep moving one over the other, and you see they will match again after 7 days. Okay, then you move, keep moving the mass. So the formula is that you have this data is x of n. You multiply it with its shifted version, xn minus k. Okay, and then you add all the values, and k you keep varying k from n, sorry, keep varying n, and you get autocorrelation x of k. So once k is 0, you multiply xn with xn, signal with itself. So definitely it is going to give you the maximum value. Once the signal gets multiplied by itself, just square of every value and it's going to give you the maximum. But as you move, k is equal to 1 means that you have this signal here, and the next you start from here and go to the here. Okay, and then once k is equal to 2, you go to the next and next. So same signal, you have 2 copies of the signal, one here and the other one you are moving, and it is going to see another peak once you are 7 days or 6 days, move 6 days the other, and you again see a peak. So if, because this is just a random data, so you are not seeing any pattern here, but if it is a real data, you see a pattern. Okay, so this is the autocorrelation, where by itself you are checking the cyclic nature of the data, seeing whether you see this, like I told you about and the autocorrelation will tell you that how autocorrelation refers to degree of correlation of the same variables between two successive time intervals. It measures how the lagged version of the value of a variable is related to the original version, lagged version of the same. Okay, so you can you have the autocorrelation and cross correlation with something else, but this is how I was plotting this autocorrelation. I asked it to generate um, data of the customers, and it is showing you this because I don't have data on the left and data on the right. But if it is a hotel, then you have data for all these days. If it is 100 days, if it is 100 days, so it is assuming that there is nothing here and there is nothing here. But as a matter of fact, there is going to be some data here as well and here as well. So once I start from here. So I have this overlap as well. So, but you see this little cyclic nature because I asked it that for Sunday and Monday, it's a very interesting chat GPT. So I asked it to have more people appearing after every 5-6 days, so Sunday, Monday more. And you may also, so this makes me believe that, so this is a cross correlation, that there is maybe any correlation with lunch high tea in, let's say, in Marriott, if you have data that. Okay, you say I am Serena and I want to see whether the same pattern is appearing in another hotel or not. If you have the data, you say perhaps the same pattern. There must be reasons, other factors that people are coming more to have to dine out and stuff. Okay, so this is a startup idea that actually I think that we can make a very interesting utility for hotels and restaurants. And all you need to have is stochastic modeling of the restaurants for prediction, decision aiding, promotion campaigns. They run a campaign, then they can see that is there any effect of the promotion that they have run, maybe 25% off on this credit card or that credit card. So that's why they run. And when do they actually require to run a promotion if they're seeing a less sale, less people coming in? And so room booking, restaurant, weddings, food, these are the, so you can have all of this. and collecting all type of data, the customers, the demography, the age, the coming with the family, who eats what, external factor, there are conferences, there are events, there are wedding seasons, there are Ramadan, the weather, the economy, the tourism, the travel advices. These are the external factor that you can factor them in if you are developing such an application. And you can just tell them that if there is going to be a conference or an event in the city, this is what you're going to see. This is what our data is telling. You can make this a data driven by having all these factors factor into your stochastic model, and have a stochastic model for them to actually see on a dashboard that this is what the data is showing. And there is a drop in sale, drop trend, increasing trend. And this may not be for anything to do with the hotel, but maybe because of the external factors. Maybe the economy is improving, now people have more money. Okay, there's a gas load shedding, so people have no other option but to go and eat outside. So things like that. So external factors you put in, but make it into a stochastic process. And this is where you need a cross correlation. So there is the conference is happening is another random variable. Okay. And so if there is a correlation between a conference happening and you are seeing more people, so it means they are related to each other. If there is a wedding season and you are seeing more people, or Ramadan, you are seeing more people coming for the iftar, and so they are related. But it could be a very, very interesting application. But I have not seen any which really does all of this. There are few, like you can book your room and you can do this or you can do that. I have not seen anything, but they have like big businesses. And in Pakistan, there are few hotels, but I've seen like in Dubai, for example, there are hundreds and thousands of hotels and restaurants. So is in Saudi Arabia, everywhere. So if we can have like something very, very strong, I think it's a big market for such an application, because hoteling is such a big business in almost most part of the world. So now it brings me to another very interesting topic where we dedicated this week to Mr. Shannon as the information theory, and how basically it is applicable in artificial intelligence. Okay, so information theory is about measuring uncertainty. That if you're not certain about something, so how do you measure uncertainty? Can you actually measure uncertainty? So that's something very interesting, that how you could relate uncertainty with the measurement. And so as it reads, entropy allows us to make precise statement and perform computations with regard to one of the life's most pressing issues, not knowing how things will turn out. Okay, so you can have a measure on uncertainty, you can assign a number, and we would see that how you do that and how it relates to machine learning, AI, and all of that. So now again, we need to, because it's building up on the same concept that you have a sample space where whatever you are studying, so there are a finite number of outcomes of what you are studying. Okay, so finite number of outcomes may have, because once you have more options, it means there is uncertainty into the whole thing, because you don't know that how this whole thing is going to turn up. So once you have multiple options, it means there is uncertainty in what you are going to see. So it's about that modeling uncertainty, first of all, as a random variable. Important random variable has to model uncertainties if you want to study and you want to deal with uncertainty in decision aiding and whatever you are doing. So for it has to be modeled as a random variable, and we know random variable is nothing but you make a sample space, make all the possible outcomes part of the sample space. If it is voting, as we earlier said, if it is voting, you say a person can come vote to Jamaat Islami or PTI or PPP or ML, Muslim League, and any other. Any other means those are not very significant. So I'm not really concerned. And so if, let's say, I'm establishment or I'm doing something for the establishment, interesting study, and I want to develop something, an application, a tool, which actually is based on AI and machine learning, for them to do the engineering of the elections, for example. And how do you do engineering? So we can very easily do very good engineering on things, and so I start building onto a political engineering tool to ensure that you reduce the uncertainty in the elections, for example. Okay, so this is totally non-political. So, okay, though it is political engineering, but it's not that just making any political statement. But yes.
How can we differentiate between probability and uncertainty of our data?
Yeah, that's what we are going to study. That how do you relate probability with uncertainty? Okay, so let's see that. So, so if you are an establishment like I am, for example, and I want to have least uncertainty. Okay, so I'm just say I want to be least uncertain. Let's say if I collect some data and I find out that uh, anybody can win. So this is very uncertain. I don't like this situation because I don't know whether it is going to be Jamaat-e-Islami or PTI or Muslim League Noon or PPP, because everyone has uniformly distributed, everyone has equal chances of winning. Okay? So this obviously I don't like because a lot of uncertainty. So uncertainty is that if every outcome is equally likely, so that is the most undesirable thing, because a lot of uncertainty, because I don't know, I cannot prepare myself because every outcome is possible. Okay? So this is the maximum amount of uncertainty you can have. If you go to a hospital, you can have any kind of disease. So maximum uncertainty, you are not sure how to deal with it. So dealing with this type of uncertainty is the most difficult, where anything could happen and everything is equally likely. Okay, so this is very uncertain from planning perspective. And I see, okay, let's say I want to do some political engineering to make the what I want. Let's say Muslim League Noon to have half of the seats, but still I don't like it, because I say, yeah, still if PTI joins hands with PPP, then still, so still there is uncertainty, but this is better than the previous one, that I have like half of the seats going to Muslim League Noon, but still there is some uncertainty, but better than the other. But what if it is like this? So I am the happiest person, as for example, if I'm doing, I say, if I am certain that, I'm almost one, not really exactly one, but one means that it's the majority, and you say, and sometimes you say, no, it should be like, if I'm establishing, I say, no, let us divide and rule. So you have some leverage, or even you may like to, it depends that what, and you may like even 1-4, 1-4, 1-4, and then you see that how you can do the political engineering. But so if it is in my hand, I say perhaps there is no surprise, so I'm comfortable. I can deal with now this, because I know. So this is the least uncertain. This now you are certain that this is what will happen. So measuring uncertainty, this is what Shannon has actually proposed, that to measure uncertainty of a random variable x, so this is what is x in our case. This is that who you vote for. So you vote for 0, or you vote for PTI, or you vote for Muslim League Noon. So there are like 4 different options. So random variable can take value 0, 1, 2, 3, 4, and everything has a probability. And the probability may be your belief that this is how it is going to happen, or probability may be from the previous data, or probability may be from the surveys that you are getting. And actually, we predicted the last election, we very precisely predicted from OSINT, from open source intelligence, seeing what people are saying on Facebook and Twitter and blogs and this and that. And we could able to actually figure out about with 95 to 98% certainty that this is how the results are going to be turned out in Pakistan on the election, almost, because a sample space, and let me show you some very interesting study that I have done on the American election, starting from 1964 till today. So here is this is a negative minus sign, because probability is less than 1. So once you take log of this, is going to be a negative number, which is less than 1. So you just want the uncertainty to be a positive number, so that you can gauge that how uncertain you are about a sample space, about a system that has multiple outcomes and the probabilities of those multiple outcomes. So it's very simple formula. You have the probability of each multiply by the log base 2 of that probability. So it's that simple. Okay. So for example, here is so this is again interesting. Like you have uh, a coin which has a head and a tail. It's a fair coin. So once you toss it, so you may get a head or you may get a tail, and it's a 50-50% chances. But like film Sholay, if you have both sides are head, okay, so there's no uncertainty. You know, whenever you are going to flip a coin, you're going to get a head, right? So there's no uncertainty. There's no surprise here. There's maximum surprise. You don't know whether it'll turn up head or tail. So there's a surprise. So once you compute its entropy, okay, half, and so this is minus half log base 2 of half and minus half log base 2 of half. So we know this 1 over 2 is 2 raised to the power minus 1, and power and this cancels out, so you get minus 1. So you have minus half into minus 1, and here minus half into minus 1. So you get half and half, and you get 1. Okay, so this is your answer. So for a sample space where there is only 2 possibilities, the worst you can get is for uncertainty is 1. The worst you can get as an uncertainty is 1. It is always 2 raised to the power something. So 2 outcomes mean 2 raised to the power 1. If there are 4 outcomes, it is 2 raised to the power 2. So it's going to see 2 as the highest uncertainty. So if there are 8 outcomes, you are going to see 2 raised to the power 3 as 8. So the maximum uncertainty will be 3. So it is always 2 raised to the power something that will give you the maximum uncertainty in that event. So you say maximum uncertainty is 1. So but what if both are head? So both are head. So you have 0 and 1. And as we know, log of 1 is 0. See, this is 2 raised to the power 0 is 1. So log of 1 is 0. So you get 0. So 0 means that you are 100% sure that what is going to be the outcome. So in machine learning, we want to get, once we are doing classification, for example, for every class, I want that in that class only those things should be there. So once I start the classification problem, I may have maximum uncertainty. Like diabetic patient, I have 50% patient who are non-diabetic and 50% who are diabetic. So there are 2 possibilities, and I have a sample space with maximum uncertainty that every other person may or may not be diabetic. So this is the maximum uncertainty. And once I classify them, and I could actually separate them. So I must get in this class the uncertainty to be 0. That is the ideal. And this class uncertainty to be 0. So means that the entire AI machine learning, once doing the classification, it is going for high uncertainty. And as it keeps moving down, it wants to go to 0 uncertainty, that there is no uncertainty. Yeah. All the things which have fallen here in this branch are actually one type of objects. These are another type of object. These are another type of object. So most of these algorithms, they basically try to minimize uncertainty into that group. So they are trying to minimize the uncertainty, and you try to if like we'll study if it is a decision tree, so you try to take first step where you can reduce the uncertainty by maximum, okay, because there are so many options for you to take, routes for you to take. So you say I'll try to maximize the amount of uncertainty I can reduce by moving from where there is maximum uncertainty. And remember, maximum uncertainty is depending upon how many options you have and what is the probability. If it is half and half and 2, so maximum certainty, you have all these outcomes are equally likely, so which is obviously not good. So this is where we set a random variable, and this is now I am doing the political engineering, so I just want to see how much uncertainty is going to be there if this is the scenario where people are voting in this ratio. So I simply put the numbers here, and which is minus half log of half and 1 over 4. And so I find out it is 1.5. Right? So I know for 4, it is 2 raised to the power 2. So it is 2. Maximum certainty is 2. So it is better than 2. So I said, okay. But here, if it is everything is equally likely, anybody can win. So I don't like this because I'm taking a lot of risk. I don't know who is going to be in the government. and here the maximum uncertainty is 2. So my job is for somehow to reduce this 2 to as minimum as possible, so that I have certainty that this is what I want in the election. So no matter what I want to do, I'll try to do that to ensure that I have something which is closer to 0. So I know that this is what to be done. Okay, so there is no surprise. Like if this is the case, and so here the uncertainty is 0. Okay, uncertainty is 0 because I say so everybody is going to vote for Muslim League Noon, and for that I may have to just do something with all the other parties. Okay, you have only one option to vote. So I have actually here is the code. I think I should show you the code as well, what I have been. So here is the code for this is where I have generated the models. Okay, here's the model that I've generated, and I'm changing the epochs, and so, and every time I am just plotting the. So here is thing. The other thing that I have, the autocorrelation and correlation. It's all generated by ChatGPT. So all these are the things that I've been prompting the ChatGPT to generate this for me. Okay, so I'm just making sure that everything. And if you have, like, I got an error, so I would just paste it in ChatGPT. So I'll just fix it and say, okay, so generate Python code that implements a GAN for learning a distribution from 1D sample data, and then generate new samples from the lead. So this is what it has generated. But once I actually ran it, it gave me an error. Okay, so I put that error back into ChatGPT. I said, this is the error I'm getting. I only copied and pasted that error. And it says, I apologize, the error in the code. It looks like there is a typo in the super call. And so every time getting an error, pasting, and finally it returned me something which actually works. Okay. And so I have the same thing generated a code here. I only ask it to generate where I could give different possibilities to events. So I can just here increase the events A, B, C, D, E, F, G, H, and I can have the probabilities. Here I have the most certain 1, 0, 0, 0, but I can have 0.5, 0.2, 0.1. I just need to make sure that once you add them up together, it should come out to be 1. So it'll just calculate and it'll give you all the entropies. So the goal is obviously to all the AI machine learning is, or maybe the goal of life is also to minimize the uncertainties in life, that not every event should be equally likely. And so this is where if you have 6, so they are equally likely. So it is not 8, not 4. So the worst is 2.58. Okay. And interestingly, if you have uniform distribution has the maximum uncertainty. Okay, so we know that. And so this is how the entropy changes. Like, for example, this is the case of communicable diseases, a COVID. Let's say there are 10 people in a house and nobody is COVID positive, so you are happy because here is the. And now people start getting COVID, so uncertainty of finding out who has the COVID and who does not, here it is maximum because every other person has COVID, you don't know who does not. So and now here everybody is COVID positive. There's no uncertainty. So everybody you pick is going to be COVID positive. So you got to be away from that home. So these are the cases you can do the reading by yourself. And then if you remove the P from here, so it is called the number of bits to require to present a piece of information, kind of. So this is called self-information. But for us, more important is the entropy. And we know that we start from here, and objective is in a specific class. We want to move where there is a only one type of subjects. Okay, so machine learning is to move from high entropy to low entropy. So this is ideal. If you could, like PCA was doing this for us. We saw data which is mingled with each other, and use the principal component analysis, it would try to separate, find out the a way to basically changing the axis, and would try to give you from high entropy to low entropy. And if you have two random variables which are not related to each other, like the experiment we did, and I said the winner is who would have a head and who would get 6 on the dice. So now I have joined two uncertainties together. Okay, one is flipping of a coin, the other one is rolling a dice, and I'm saying the winner will have this, and both are equally likely. So you add the uncertainties if you have uh, independent events, and if you have joined and conditional. So because whatever we have learned in probability, the same you are going to put it here. Like this is where you have joint probability. What is the probability of you getting a 6 and a head? Okay, so 1 by 6 into 1 by 2, it is 1 by 12. So it is, the probability is 1 by 12. So now there are more options. In once you are flipping a coin, only two options. So worst is 2. If you are rolling a dice, there are 6 options. So worst is 2 point something. But now there are 12 different options which are here in the table. These are 12 different options, and all are equally likely, which is 1 by 12, 1 by 12, 1 by 12. So you're going to have more uncertainty. And same is the case with conditional entropy. Whatever we have learned about conditional entropy, you open the log and you have the formula. This is if they are independent events, then uncertainty of one event and plus uncertainty of the other event. You've got to add them together to get the uncertainty. If there is a mutual information, with information of one helps you to reduce the uncertainty in the other. Okay, so there may be cases, as I said, Pakistan losing the toss with a match between Pakistan and India. So now knowing that Pakistan has lost the test, so you know now there is less chances of winning, especially with the South Africa as well. That though they won the toss, but still they lost. But for sure, because the way South Africa is playing, we know that if they bat first, they are going to score about 400 runs. So knowing something is the mutual information, and knowing something then would have your mutual information is the reduction in the uncertainty of X due to the knowledge of Y. You know that Y has happened, and so you say, okay, now you can, it improves the uncertainty. This is the so want to start with the decision trees. I think we can cover a little of this. I think this is perhaps kind of the most logical way of doing decision making, and that's how we do the decision making. If you want to buy a car, okay, and you see, okay, I have only this much money, so I'll buy a car if it costs me about 50 lakh to 60 lakh rupees. So first is, if something is more than 60 lakh, so I say I don't even consider this option. So you come down, you say, okay, it has to be less than this much. And then you say, okay, if I'm buying a second-hand car, I say it should not be very old, must be maybe 2020 or 2019. Okay, so in your mind there is always a decision tree which is happening in every person's mind once you are taking a decision. Okay, that decision tree, you traverse the decision tree, and sometimes you take strong decision because of that you have not run that decision tree while you were taking decision. Okay, you are marrying your kids, you are marrying yourself, you are selecting a university. Everything is a decision you take based on, and perhaps you don't write them as a decision tree. It's better that you write them as a decision tree, that this is how. But this will help you to even take your decisions in life based on that the uncertainties and what you want to do, and the probabilities, the chances, and so you can make a decision tree, and then you come up with a decision through a logical way. So decision tree would help you to do that. And the more interesting is that you take previous data where people have taken decision. For example, the doctor deciding that this person is going to have a heart attack, so he must be admitted in the hospital. So they must have seen several they must have seen the data, and based on the data they would decide that this person should be given this medicine or this kind of a treatment or this or that. And from that data, where you have all the parameters, generating a decision tree, that is even more challenging and interesting problem, where there is no decision tree, but there is a data where people have taken decision. Okay, people have bought cars, but you don't know what inspired them to buy a specific car. But you know about their data, you know their demography, you know their family information, their income, their this and that, and then you extracting perhaps the logic which people have used to buy a certain car. That is the most amazing part of this. That so you extract from the data the decision tree which people may have to basically even, and it is for any decision you take. Maybe you go and vote for somebody, maybe you buy a plot in B17. So there's always a decision making, and what we are saying is that you are doing the inverse problem. You're solving an inverse problem. You're saying I have the data and I want to get into the minds of the people to find out that what decision making has happened for them to take this type of a decision, right? So you go and you extract that tree is the most interesting part, and that's what we are going to learn in this part, that if you have the data and with all the parameters which matters in taking a decision, okay, and the value of the every parameter, and then you extract a decision tree out of that, that perhaps this is what the most logical way the people must have thought in their subconscious, maybe once they took this decision. So that makes this decision tree very, very interesting. But for others, maybe it is very the way that actually they make a decision tree. If they want to give a loan, for example, bank giving a loan to somebody, so they can like figure this out by just finding out that uh, why should they give it? This I've taken from the internet, the study.com, and this is from Edureka, because such a elementary and basic technique that you can find a lot of material, at least just making a decision tree like this, that if you have want to see, you have some spare time, and in our case, that the friends visiting, you may want to go to a cinema. If you're not going there, you check the weather. If it is sunny, you may play a tennis. Obviously not for us, we don't play tennis, and if it is sunny and rainy, stay in. We don't stay in if it is rainy. And if you are rich, you go for shopping, and if you're poor, you go for movies. Obviously, this dysentery for sure is not for us. Okay, but we can extract a decision tree like this for our population. As I'm saying, if you people are doing things, people are going watching movie, eating, okay, and eating samosas or eating in Serena, or you can exactly extract the decision. So so these are like, but mostly this is how the whole thing works. That you have a training data. And this is what I'm saying, you extract a decision tree out of the data. So you have the training data and you make a decision tree, and then you check on the test data that really this is how the people have made decisions based on all the parameters you have. So this is what a decision tree is. It is supervised learning. Why? Because you got to have annotated data that this person has taken this decision, this person has taken this decision, and based on this data, this decision was taken. So it needs it's a supervised, and once you are constructing, and this is the method that you construct based on the information gain, that you which parameter you use, which gives you maximum information gain. You use that parameter. This is important. That if you use, so you can make a shorter decision tree and very smart decision tree. If you measure the from the data, figure out all the numbers, all the probabilities, all the options, okay, and then based on that, you can extract that perhaps this is how they have taken the decision. The decision making can be extracted from the data, and you can have, as I mentioned earlier, I was in Dubai, and we had a flight with PIA, and we went to the airport, and we only found out that the flight was cancelled. Okay, we were at the airport, and there was nobody from the PIA at the airport, and we are not. And like me, there were so many other people, and they never informed that we have cancelled the flight. Right? And then they said they are not sure even there is a flight tomorrow or not. So I came back, and I wanted to go to Karachi. So I was in Karachi yesterday. So I said, except PIA, any flight which is going in the morning. So very easy decision making, that it must not be PIA. So here the information gain is maximum, that the probability of I traveling on PIE, at least after this Dubai episode, the next day, it's not going to happen. So the first decision branch is that not PIE. So now you start exploring other options, the timing, which one is the earliest, how much is the fare, and so you basically do the decision making like that. So you have a root node, you have the interior nodes where you are taking the decisions, and ultimately you are coming on the leaf nodes where you take a decision. So sometimes decision is as simple as this is. I said PIA, not PIA. Okay. So there is just on one parameter, you say if height is greater than this, height is less than this. So, and if now it becomes a little difficult problem, but still you can say first decision is if height is greater than this. So you have green, but the other branch still you need to decide. And you say if this foot is greater than this, it is red, otherwise it is green. So you are going to have another branch. So that's how you grow a simple decision tree based on the information gain. Because many of you must have studied this already, if anybody who has studied machine learning. But once I say that you have the data available, this is what is meant by that. And you say you interview people and you find out that there are like the people that, or maybe the same person, you are extracting his way of decision making. And he says if one day it was a sunny weather and the temperature was hot and the wind was low, I did not go out to play golf, for example. But then you just keep asking him questions every day. He just it is raining today, the temperature is mild, the wind is high, so I go out and played something tennis maybe. And then so you have this data available, and you have the decision, the final decision of that person, that what he did under these circumstances. There may still be something missing, some of the options missing, because depending upon the different type of weathers you may have and the temperatures and the wind types. So the data would give you a good uh, options to build a decision tree based on the information gain. Okay, so this is, so what you do is you say, what is the probability of this guy actually going and playing? Okay, and that's why the decision tree would be always going, no matter whether it is sunny or rainy. So there is no need to make a decision tree. But you find out that there is a 30% probability that he'll not go and play. So you say, okay, I'll put this here. This is the probability that he will not play. There's a probability that he will play. And because there are only two options, whether he play or he does not play, it is not 0.5, 0.5, otherwise it would have been 1. Okay, still most of the time, so information is you find out the entropy, and the entropy comes out to be 0.8812, which is not 1, which is not 0. So it is 0.8812, means that now you need to take it to branches where you get 0 almost. Okay, so you, what now you do is you split now, and this is the algorithm. You don't have to do it, but this is what the algorithm is doing, that you have split on weather. So you say weather is what, when weather is sunny. So weather is sunny, 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 sunny. Okay, so you say weather is sunny, 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 and you take the sunny, 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 and the other things, and there is only one no and rest of this yes. So you, and this is what you are calculating for every other option. You say weather is sunny, and you, the probability that weather is sunny is 0.4. So you go back, find out the probability that weather is sunny. What is the probability here of weather to be sunny? It comes out to be 0.4. And you play and not play. If the sunny, you find out it is 0.25% you don't, and 0.75% you do. So you have these numbers, and then you have what if weather is rainy. So you again go back to this, the probability that weather is rainy, you find out from here, and you come back and you say it is weather is rainy is here. So 50-50 is the weather is rainy probability 0.5, and 50-50 chance that you play and you don't play. And you come back here, and it is say overcost. Again, you say it is yes, yes. So means that you probability play is 1, 0, and the overcost is 0.2. Okay. Now you find out the weather information gain for a weather, that if you're making a decision based on the weather, the first thing, whether is sunny, this or that, that is the branch that you want to take. So you find out is information gain. So the information gain is that you add all the three together, it comes out to be this. And recall this is 0.88125. So the gain is that you are reducing the uncertainty, but by only 0.1567. Right? So uncertainty of you going play and not is 0.8812. But if you take a decision based on the weather, you are going to reduce the information. Uh, uh, your information gain is 0.171567. Now you do this for the others. For the temperature, you repeat the whole thing again. Okay, the same thing for the temperature, that there may be temperature is hot. So now this is the column that you say, no, I'll take a decision based on. The first decision is based on the temperature, and this, as you can say, 50% chance, and the temperature to be hot has this probability 0.4. And so you say mild temperature, you again do this number, and you say cold temperature, again you do these numbers, and you find out 0.68, and here the information gain is 0.2, and you go back and you say it's a better information gain. So I think the first decision, temperature, is playing a more important role in making me decide whether I'm going to play or not. Okay, and as I'm saying, perhaps you don't know, this is what the machine learning AI is helping you to figure out, that actually temperature has a bigger role in your decision making. And perhaps you yourself are not sure about it, but it is. So you do this on the base of temperature, and then you go and say wind, and you say, okay, now the wind is low. Okay, you calculate this, and wind is high, you calculate the information gain, and then 0 point, hardly any gain. So you say, no, perhaps the wind is not really going to change, give me information gain. So once I make a decision, I'll make it based on the maximum information gain, which is the temperature. Okay, so you have the maximum information gain for the temperature. So you make so this is you make a classification tree where though yeah. So this is where you check first the temperature, then the weather, and then the wind. Okay, so we'll come back and we'll just cover this, that the first decision is your based on the temperature, that what the temperature is going to be. It is hot, it is mild, it is cool. And then you go to the next node, and where you again and the wind is the last thing that you are going to use, because most of the time you may just get to a zero information gain, a zero edge, that you definitely are going to go and play. But once you have hot, still there is an option whether you go or you don't go. And if it is cool, still there is two options. It is so that's how you develop a tree. So next time we come back and we will do this, cover this, and this is just very quickly. Perhaps next time I'll show you PhD work of one of my students, where we have what the medical education has done is that they have built all these decision trees. Okay, based on that, how do you take a decision? For example, about a person who has come to the hospital with a cardiac issue. This is, and they are called these clinical pathways. So based on all the knowledge, all the information, they have develop all these charts, and these are called clinical pathways. Okay, so a person comes with a chest pain. Okay, so the decision is that you think that he may have ACS, and then you ask him to go and get an ECG done. So he gets an ECG done. This is STEACS, STACS, whatever it is, and this is basically out of the ECG. Either it says that you have this or no. If you have no, then you go for another test, which is says troponin. If it is yes, then you diagnose it to be STEMI, and you say this is the treatment that you need to take. So these are the decision trees which are already being developed. How the same thing which I told you. There's a lot of humongous amount of data that you have, and then you can extract a decision tree out of that. And what we have added is that based on this is done by mostly Western countries. In our country, once a patient comes, he not only comes that he has the pain in the chest, he may be sweating, he may be apprehensions, he may be shortness of breath. And we have seen that, and we got a lot of data, and we did frequent pattern mining, uh, and then we fused the two to upgrade all these. So we developed a methodology where we can upgrade, localize the clinical pathways based on our practices, the practices which are done by our good cardiologists, which may not even go and see that what is the clinical pathway. And this is for normalization, that for every doctor, if we give them that this is what the best doctors are doing, and this is how they treat a patient. So we can have a good, this we call this computerized physician order entry. So we were developing a machine learning based the computerized physician order entry based on the best practices of the best doctors, augmenting what is already being published, and we add into those. So this is what we augmented one of the clinical pathways, where now once they see that troponin is positive, then they have this diagnosed, not only STEMI, there is something else, and STEMI, and then they have different type of treatments for that. So augmentation on a clinical decision support based on the current data and how you go about doing this. So this is perhaps, so next time we come, we will complete the decision tree, and we move to the another thing which is the clustering, but clustering is primarily the base of generative AI because it is unsupervised learning. So we'll do that.
It would be the difference earlier information either between two entities.
देखिए ये था कि आपने आप उससे डिसीजन ट्री नहीं पूछ रहे, ठीक है, आप एक बंदा लेट से गोल्फ खेलने जा रहा है, ठीक है, आप उससे कहते हैं कि यार कुछ डायरेक्ट मेजरमेंट्स ले रहे हैं, कुछ इनडायरेक्ट कर रहे हैं, ठीक है, आप यू नॉट इवन आस्किंग हिम. फॉर एग्जांपल आप कहते हैं मैं खुद ही से मेरे ख्याल में ये पैरामीटर्स होते हैं, ओके, एंड यू आर जस्ट कलेक्टिंग दीज पैरामीटर्स. आप कहने अच्छा उस दिन सनी भी था और यूं था ये था लेकिन नहीं गया खेलने, ठीक है, अच्छा इस दिन चला गया खेलने, इस दिन चला गया, एंड यू योरसेल्फ नो कि ये फैक्टर्स हो सकते हैं उसके डिसीजन मेकिंग में, एंड यू आर नॉट मिसिंग एनी, ठीक है, तो आप उसको बता सकते हैं कि दिस इज हाउ यू आर टेकिंग डिसीजन, दिस हाउ पीपल टेक डिसीजंस. इसी तरह जैसा मैंने कहा कि हमने जो क्लिनिकल पाथवेज हैं, अब डॉक्टर हैं वो एक्सपीरियंस से सीखते जा रहे हैं, ठीक है, 5-10 बंदे मैं कहता हूँ मारते हैं फिर वो अच्छे डॉक्टर बन जाते हैं, सो दे आर लर्निंग फ्रॉम देयर एक्सपीरियंस के यार. And this is what people have learned in COVID as well. By experience, they are learning. And now they are good doctors. Once they are good doctors, they are practicing, which we believe is the best practices, because एक डॉक्टर है, हर पेशेंट उसके पास जा रहा है, इट मीन्स कि वो द बेस्ट डॉक्टर है. अब आप उसका जो भी तरीका है ना, उसका डेटा आप सिर्फ कलेक्ट करते हैं कि वो क्या डिसीजन लेता है, कौन सी दवाई देता है, कौन सा टेस्ट लिखता है, कौन सा ये प्रिस्क्राइब करता है, सही है, उसको भी नहीं पता, बट उसको उतना एक्सपीरियंस हो गया है कि वो ये डिसीजन ले रहा है और ये नॉलेज सिर्फ उसके पास है, ठीक है, ये नॉलेज उसने ना किसी को दी है ना वो किसी को देना चाहता है, फॉर एग्जाम्पल. लेकिन आप कहते हैं यार कोई बात नहीं है, तू ना दे, हम खुद निकाल लेंगे इसमें से, सही है. आप क्या करते हैं, आप पेशेंट का डेटा कलेक्ट करते हैं और उसको देखते हैं यार उसने इस डेटा की बेसिस पे उसने कौन सा टेस्ट लिखा था, ठीक है, और फिर उस टेस्ट का क्या रिजल्ट आया था, उसने कौन सी मेडिसिन दी थी, कब उसने कहा था कि अब इसकी ओपन हार्ट होनी है, कब उसने कहा था ये होनी है, ठीक है, तो उसके डिसीजंस आप लिखते जाते हो. एंड इफ यू हैव डेटा अबाउट 10-15 गुड डॉक्टर्स, आप कहते हो अब मैं इसमें से एक डिसीजन ट्री एक्सट्रैक्ट करूंगा और ये मैं जो जूनियर डॉक्टर है ना इसको अपनी सॉफ्टवेयर में बिल्ड कर दूंगा. That's what we were doing. I'll build it into the software that he will not able to give any other medicine which is not prescribed by the best doctor. I'm not going to give a test जो कि किसी बड़े डॉक्टर ने नहीं लिखा, जो कि बेस्ट इन दिस फील्ड है, तो आपने उसके हाथ पैर बांध दिया कि यार तुमने ये टेस्ट तो नहीं लिख सकते इसमें, अगर ये लिखोगे तो फिर आगे रीजन दो कि व्हाई यू आर राइटिंग अ टेस्ट, यू आर गिविंग अ मेडिसिन टू अ पेशेंट जिसकी जरूरत ही नहीं है, सही है. तो आप ये क्लिनिकल डिसीजन सपोर्ट सिस्टम बना लेते हैं और ये अमेरिका में they call this they have these standards के जितना बड़ा हॉस्पिटल होगा उतनी नॉर्मलाइज होगा वो, यानी कि you go to a junior most doctor, you go to the senior most doctor, you get the same type of treatment. Why? Because they have these softwares which ensures कि आप इस तरह की कोई चीज ना प्रिस्क्राइब कर रहे हो जो कि वो डाटा नहीं आपको कह रहा। अच्छा, मुझे ख्याल है मुझे मीटिंग के लिए भागना। थैंक यू वेरी मच दोज हु आर ऑनलाइन। मैं शायद अभी कोई क्वेश्चन ना ले सकूं, लेकिन इंशाल्लाह नेक्स्ट टाइम वी कम विल स्पेंड अ लिटिल मोर टाइम ऑन द research that I have done with my student, and anybody who wants to extend it can also extend it. Thank you very much.